Hey everyone, welcome back to another lesson in MCV4U. Today we'll be looking at the first lesson in optimization. So here, one of the most important applications of derivatives occurs in the solution of optimization problems in which a quantity must be maximized or minimized. Now, here we're going to outline the steps for solving these types of optimization problems. First step is to make a sketch and label the quantities of applicable. Define all variables with let statements. The second step is to identify which quantity must be maximized or minimized. This quantity is the key variable. The third step is to write an equation for the key variable. We will call this, in this situation, the key equation. If the key equation contains more than two variables, use other known information to sub into the equation so that the key variable is expressed in terms of only one other variable. The fifth step is to take the derivative of the key equation with respect to the other variable in the equation. Step number six is to use the algorithm for extreme values on an interval to find the maximum or minimum value. Remember that you have to consider points where the derivative is zero as well as the endpoints of the domain of the function. And then the seventh step is to write a conclusion, including units. I want to cover one thing here in terms of the extreme value theorem. So if the function is continuous on a closed interval from a to b, then the function has both a maximum and minimum value on the interval. There will always be an absolute max or min on a closed interval, which may be from a critical number or from an endpoint. Okay, so let's take a look at this first example here. And this first example says a cylindrical tin can is to be made with 500 centimeters squared of tin. Find the maximum possible volume of the can. So here, we're given a piece of information and we're given 500 centimeters squared. Here, we know that the 500 centimeters squared provides us with the surface area. And so here, if we draw ourselves a diagram, so here we have the diagram of the cylindrical tin can. That we have our radius and we have our height. So again, the first step that we're going to do is we're going to create some let statements. So we're going to let h represent the height of the tin can. And this is going to be in centimeters. We'll let r represent the radius. Of the base of the tin can in centimeters. We're going to let SA be the represent the surface area. And this is going to be in centimeters squared. And then finally, we'll let V represent volume in centimeters cube. Okay, so a couple equations we want to start off with. So the surface area equation for the cylinder is 2 pi r squared plus 2 pi r h. I'm just going to box this so we have this formula with us. So we know that the surface area is equal to 2 pi r squared plus 2 pi r h. And here we know that the surface area is equal to 500 centimeters squared. So we can sub that in. 500 is equal to 2 pi r squared plus 2 pi r. Here, if we move the 2 pi r squared to the other side, 500 minus 2 pi r squared is equal to 2 pi r h. Here, what we're going to do is we're going to divide both sides by 2 pi r. So when we divide both sides by 2 pi r, we can simplify this, and we'll get h is equal to 500 minus 2 pi r squared over 2 pi r. And here we can write this as two separate fractions. So we'll get h is equal to 500 over 2 pi r minus 2 pi r squared over 2 pi r. This here we will be able to simplify. And here, this will be simplified as well. And so here we get h is equal to 250 over pi r minus r. So here again, h is equal to 250 over pi r minus r. Now that we have isolated for this variable of h, the other equation we have is we know that volume is equal to pi r squared h. So let's box this as well as another formula. So we're now going to sub in what we just found as h into our v is equal to pi r squared h. So here we can rewrite this as v is equal to pi r squared, and our h value is 250 over pi r minus r. So what we can do is we can distribute the outside to the inside. So distribute the pi r squared into 250 over pi r and negative r. So here we'll get volume is equal to 250 pi r squared over pi r, which will be simplified, so do in a second, minus pi r cubed. So here we can simplify pi r, and so here we'll be left with volume is equal to 250 r minus pi r cubed. Now the next step here is that we're going to derive this v is equal to 250 r minus pi r cubed. So here v prime is equal to 250 minus 3 pi r squared, and now we're going to make it equal to 0. So here we have 0 is equal to 250 minus 3 pi r squared. We'll move the 3 pi r squared to the other side. So 3 pi r squared is equal to 250. And r squared is equal to 250 over 3 pi. Therefore, r is equal to square root 250 over 3 pi, which is approximately 5.15 centimeters. So here, to check, again, to check here, we're going to perform the second derivative second derivative test. So here, in order to check, we must perform the second derivative test. So here, the second derivative is equal to negative 6 pi r. And so here, we'll do our number line. And here, we'll go from 0 and to our point that we have, a critical point, which is at 5.15. So here, if we sub value that's in between, let's say we sub 2. So here we get negative from the negative 6, positive from pi, and then for r, which is 2, which would be positive. So that gives us a negative, which means that it is concave down. And so here that confirms to us that, therefore, the maximum occurs at 5.15 centimeters. So that's when r is equal to 5.15 centimeters. So, and this would be, again, the max, where the maximum volume is. Okay, so now we're going to sub that back in into our equation. So we have V is equal to 250 R minus pi R cubed, and we'll sub in our value of 5.15 to find what value the would give us the maximum volume. So here, if we sub it in, we get 250 times 5.15 minus pi 5.15 cubed. And calculate that, get volume is equal to 859.39 centimeters cubed. And so here, again, the maximum possible volume of the can would be 859.39 centimeters cubed when the radius is equal to 5.15 centimeters. Okay, so let's look at this next example here. It says, a farmer plans to fence a rectangular field next to a river. The side of the field along the riverbank does not require fencing. The two sides of the field that are perpendicular to the river must be made with a rust-resistant fencing material which costs $9 per meter. The length of the fence parallel to the river can be made with a standard fencing product which costs $7 per meter. The field must have a total area of 400 meters squared. So that's important. So must have a total area of 400 meters squared. The width of the fence must be at least 5 meters, but no longer than 10 meters. What dimensions will minimize the cost of building the fence? And remember here, the ends must be checked. So first thing here, we'll draw our diagram. So here we'll have our river in blue, and we know that we have our fencing. So we're fencing on two sides. Then we have that other side as well. Okay, so here, a couple pieces of information we want to write down. We know that the total area must have an area of 400 meters squared. We know that the two sides of the field that are perpendicular must be made with a rust resistant fencing material, which costs $9 per meter. And then the length of the fence parallel to the river can be made with standard fencing product, which costs $7 per meter. And then we also know that, again, in terms of the length, again, the width of the field must be 5 meters, but no longer than 10 meters. So here, at least 5 meters, no longer than 10 meters. Okay, so let's create a couple of let statements here. So here we'll let W represent the width of the fence in meters. And here, again, it has to be between 5 and 10 meters. Here we'll let L represent the length of the fence in meters. We'll let C represent the cost of the entire closure. This is in dollars. And then we'll let A represent the area of the entire closure. And that's in meters squared. And so again, we know that area is equal to 400 meters squared. So let's just rewrite that again. Area is equal to 400 meters squared. Here we know that length times width. So length times width is equal to 400. Here we can rearrange so that width is equal to 400 over the length. Okay. The other thing we know, so let's just box this here. So the other thing we know is the cost. So we know that the cost is equal to 9, and there's two of them, so 2 widths plus 7 times the length. And so here we know that the cost is equal to 18W plus 7L. And so that's another equation we also have. So here let's sub in our width is equal to 400 over L into this cost equation here. And so here we can rewrite it as C is equal to 18 times 400 over L plus 7L. Here we can rewrite this as 7 to 7,200 L to the power of -1 plus 7L, which is equal, again, we can rewrite it as 7,200 over L plus 7L. And so here we're going to define the derivative of C. So here we have C prime is equal, so here we have C prime is equal to negative 7,200 L to the power of -2 plus 7. We're going to make this equal to 0. So 0 is equal to negative 7,200 over L squared plus 7. Move the 7 over, we get -7 is equal to negative 7,200 over L squared. Here we're going to divide. We're going to cross multiply first. So move the L squared over. Here we get -7 L squared is equal to negative 7,200, and we're going to divide both sides by -7. Here we get L squared is equal to 7,200 over 7, and we're going to square root both sides. So L is equal to square root 7,200 over 7. And that gives us approximately 32.07 meters. Here, if we sub it back into the area equation, so here we have area is equal to 400 is equal to length times width. So here, if we sub in 32.07, we get 400 is equal to 32.07 times width, and width is equal to 12.47 meters. Let's just box these answers here. Okay. So something to indicate here is, again, since W, so since we know that, so since we know that W has to be between 5 and 10, here we must check cost for two cases. Okay, so here it's the ends of the solving domain. Okay, so here we'll take a look. So here we'll sub in the width is equal to 5. So if we sub in the width is equal to 5, so here we get length is equal to 400 over 5, which is equal to 80 meters. And here width is equal to 10. If we sub that in, we see that length is equal to 400 over 10, which is equal to 40 meters. So here we're going to calculate again. So here, if we have the width is equal to 5, so when the width is equal to 5 and the length is equal to 80, let's calculate for the cost. Here we see that cost will be equal 18 times 5 plus 7 times 80, which is equal to 650. And then here, if the width is equal to 10 and the length is equal to 40, then we see here that cost will be equal to 18 times 10 plus 7 times 40, which is equal to 460. And therefore, here we see that the dimensions that we will use are when width is equal to 10 and length is equal to 40, because with the other values, the width was greater than 10, so we can't use that. And for 5 and 80, the cost is larger at $650. So here we can write, therefore, the dimensions are the width of 10 meters and length of 40 meters. Okay, so let's look at this last example here. It says, find the area of the largest rectangle that can be inscribed in a right triangle with legs adjacent to the right angle of lengths 5 centimeters and 12 centimeters. Two sides of the rectangle lie along the legs. Okay, so let's draw our triangle first. So we'll draw a nice large right angle triangle. And this is, you see that this is a right angle triangles, so we have 90 degrees. Here, we'll label this triangle here as A, B, and C. And so here we'll have our rectangle that is inscribed inside the right angle triangle. This means that looks something like this. And here we'll label this as the length and the width. Okay. And here, what we can notice is that we notice that if we look at the two triangles that get developed, so we'll label this point right here where the triangle as D, and we'll indicate where the rectangle hits the triangle over here, E. And we'll label the others where the rectangle hits a triangle as F. And so we know that the lengths are 12 centimeters from A to B here, and from B to C, we know that that is 5 centimeters. Here we know that these, the angle C and the angle E, will be the same. Here it creates a 90-degree angle triangle as well. And this is another angle, an angle A. Here we know that we can see from D to A that the, the length there is going to be 12 minus L. And what we notice is that we can look at these two as similar triangles. So triangle ADE is similar to triangle ABC. And so here we can see that AD over AB is similar or is equal to DE over BC. And so what we can write down is we can write that 12 minus L over 12 is equal to W over 5. Okay, so now that we have all of that, let's create some let statements. So here we'll let we'll let W represent the width of the rectangle, and this is in centimeters. We'll let L represent the length of the rectangle, in centimeters, and we'll let A represent the area of the rectangle. And this is in centimeters squared. Okay, and so here, again, we know that the area is equal to length times width. And so here, if we recall, again, looking at these similar triangles, again, let's just review this here. So review of similar triangles. So here we know that if we draw two triangles that are similar, and so here we'll label the first triangle A, B, C, and our side lengths A, B, and C in lowercase, and then our angles. And then our second triangle we'll label as DEF. Here, again, our side lengths D, E, and F, and lowercase. Again, here, what we see is that angle A equal to angle D, angle B is equal to angle E, angle C is equal to angle F, and here in terms of the side lengths, we know that A over D is equal to B over E, which is equal to C over F. And here we can again indicate that triangle ABC is similar to triangle DEF. Okay, so with that being said, with the stuff that we already indicated up top in terms of the similar triangles, so we know that 12 minus L over 12 is equal to W over 5. So here, let's cross multiply here. So we get 12W is equal to 5 bracket 12 minus L. Here we'll divide everything by 12, or let's multiply this stuff in first. So we have 12W is equal to 60 minus 5L, and now we'll divide everything by 12. So here, okay, W is equal to 5 minus 5 over 12 L. And here we know that, again, our area is equal to length times width. And so let's sub the width that we just found. So we actually sub that back into our formula. Here we get area is equal to length times 5 minus 5 over 12 L. So here, if we distribute this in, the area is equal to 5L minus 5 over 12L squared. So here, now we'll find the derivative of A. So A prime is equal to 5 minus 5 over 6L. Let's make that equal to 0. So 0 is equal to 5 minus 5 over 6L. Let's move 5 over 6L to the other side, or negative 5 over 6L to the other side, which gives us 5 over 6L is equal to 5. And there, 5L will be equal to 30 when we multiply the 6 over, and so L is equal to 6 centimeters. Okay, so here, let's verify again that the length that equals to 6 produces a max. We'll write that here, and we'll use the second derivative test to do that. So verify length equals to 6 produces max. So here, if we find the second derivative, again, we see that, again, negative 5 over 6 is less than 0. And so that's concave down, which means that, again, it produces a max. So here, again, if we sub that back in to find the area, so here we have area is equal to 5 times 6 minus 5 over 12, 6 squared. We get an area of 15 centimeters squared. which will be our max area here.